let's bring on our final speaker for this stage. Alex, are you around? Let's see. Can you
Hi,
hear
yeah,
me?
I can hear you, Adam.
Alex, very good to see you. How
Good,
you
how are you?
doing? I'm excellent. I'm stoked to hear you talk. Do you have
Oh,
slides to
yeah,
share
sure, let me do it now.
of your own heart? I will be back in 20 minutes and take it away.
Okay, shall I get started now? Or okay,
Yep, you're good
okay,
to go.
cool. Hi everyone. I'm Guanhua Wang. I'm a senior researcher in Deep Speed team at Microsoft. And today I'm going to talk about how we train large language model at scale using quantization method. The project I want to talk about is ZeRO++, which is extremely efficient collective communication for large language model training. This is a joint work with my teammates at Deep Speed team. So the motivation here is as we see that the model set grows exponentially, like from originally from the birth is like 340 million parameters and goes up to recent year like Megatron Turing NLG is 530 billion parameters. So the model size grows exponentially, which means we need to use more GPUs and more parallelism to do the training. However, for a specific model, the maximum global batch size is fixed during the training. So if we include more GPUs, it means we have a smaller micro batch size per GPU during the training. So this is like our first problem we want to solve here, which is the communication overhead become huge in this small batch training setting. As you can see in this middle figure here, from right to left, as we decrease the micro batch size per GPU from 24 to 8, the corresponding communication latency or the communication time increase from 26% up to 44% in 8 microbyte size cases. So the communication latency can be huge in small batch size training. The second problem we want to tackle is the communication overhead can be really big or can be huge in the case that we have limited internode bandwidth. As you can see on the right-hand side figure, from left to right, if we decrease the interconnect between the computation node from 8 IB, here IB means InfiniBand, we decrease from using 8 IB links down to using 1 IB links. You can see the T-flops per GPU almost go down to half in 1 IB setting cases. So these are the two problems we want to tackle. First is communication is huge overhead in small batch training, and the communication can be really significant when we have limited internode bandwidth. So we want to reduce communication overhead in these two following cases, small batch training and limited internode bandwidth. So before we dive into the ZeRO++ work, I want to first give you a recap on DeepSpeed ZeRO Optimizer. So ZeRO Optimizer is an easy-to-use, memory-efficient data parallel training paradigm from Microsoft DeepSpeed team. And for training billion or trillion parameters of large language models, we usually use ZeRO Stage 3. As you can see in the bottom figure here, this is a very simple example of ZeRO Stage 3 training workflow. So from the left, before we do any computation, we need to do a forward algorithm on the width in order for every GPU to recollect the full width of a specific layer of the model. After every GPU gets the full width of a layer, we do a forward compute. And then during the backward stage, before we do any backward computation, we do this algorithm on the width for each GPU to recollect all the width of a layer again. And after each GPU get the full width of a specific layer, we do a backward compute. And then after we generate the gradient, we do a backward reduce scatter on the gradient values. And then we do a parameter update. This is like a training workflow of one training iteration using ZeRO Stage 3. So we first do a communication volume analytics on this. Basically, we have 3 collective communication involved in every training iteration. Those are denoted as those orange boxes. We have a forward algorithm, backward algorithm, and backward reduce scatter. Let's assume the model size is M. For forward algorithm on which the communication data volume will be set of M. Similarly, for backward altogether on which the communication volume is the same as forward, so it's still m. For the third part, backward reduced scatter on gradients, the size is still m because every weight has a counterpart of gradient value. So the width number of values in width is the same as number of values in gradients. So in total, for every training iteration, we need to communicate the 3m data volume given the model size of m. So how can we reduce the communication volume in these cases? We basically propose 3 different components to reduce those 3 collective communication volume one by one. The first one is called QWZ. It's to reduce the forward altogether communication volume on weights. Basically, here we adopt like a quantization method, and we communicate 8 bits instead of traditional 16 bits value, such that we can reduce the communication volume by half. But naively quantize the value can cause model divergence. As you can see on the right-hand side figure, basically we do a very simple quantize and dequantize. The final value could be, the data precision of final value could have a lot of error compared with the value at the very top. Those error values are denoted as red color numbers. So instead of doing naive global quantization, we do something called a block quantization. Basically, we first chunk the original tensor into smaller chunks, and within each chunk, we do some quantization on that. By doing this block quantization, we can achieve 3.3x data precision improvement over the baseline. And our highly optimized CUDA kernel can achieve 2.5x faster performance compared with PyTorch native kernels. By doing this quantization on the weights during the forward altogether, we can reduce the forward altogether communication volume from m down to 0.5 m. The second component is called HPZ, which is short for heterogeneous partitioning in ZeRO. This is trying to reduce the backward altogether communication volume. So in vanilla 0 state 3, when we have a full model, we split it across all the GPUs in use. So when we do altogether, this altogether will trigger all the GPU to do some communication. But instead, in this HPZ module, what we did is we hold a secondary model replica within each machine, such that when we want to do this backward altogether, the altogether only happen within a machine, not cross machine. So this is like a trade-off between using more GPU memory, but traded for you having less communication volume. And by holding this secondary model part replica within each machine, we can reduce the backward altogether volume from m to 0 because we never do cross-node communication. The third component called QGZ, which is trying to reduce the backward reduced scatter communication on gradients. The first attempt we tried is, can we just directly apply quantization on gradient communication? That is not doable because it introduces significant data precision loss due to the reduction operation. Reduction means we do a sum over an array or a tensor. So instead, we just propose a novel hierarchical auto method, which is a replacement of a traditional reduced scatter collective communication call. So we can communicate in either 4 or 8 bits, but we do the reduction or the sum operation in full data precision. And by adopting this novel hierarchical auto module called QGZ, we can reduce the backward reduced scatter data volume from m to just 1/4 of m. So the methodology summary here is we have 3 different collectives during one training iteration. And first, during the forward altogether on weights, by doing blockwise quantization, we can reduce the size from m to 0.5 m. And during the backward altogether on width, by holding a secondary replica of model within each node, we can remove this communication cost of m to down to 0. And for the third part, backward reduced scatter of communication size of m on gradients, by adopting our novel quantized collective communication call, we can reduce it from m to 0.25 m. So in total, we reduce communication from 3m to 0.75 m. Because of the time constraint, so I will only dive into the system design for the third part, the gradient communication part, which is the QGZ module. So the initial challenge here for quantization on gradient are listed as the following 3 bullet points. First is there is no existing collective for quantized gradient communication, such as Nico, Rico, they never support the quantized gradient communication collectives. Second is 1-bit atom optimizer cannot be used at 0 stage 3 because 1-bit atom optimizer assume every GPU has the global optimizer states, but in 0 stage 3 we split it across all the GPUs. Third, if we directly apply quantization on reduced scatter, can have longer end-to-end latency and lower data precision. As you can see in the bottom figure here, those blue boxes, we have 4 GPUs, G0, G1 up to G3, and they form a ring topology, and they want to do a reduced scatter. It may work as like this. So basically, after G0 receive data from G3, it will first do a dequantization locally, and then try to do a sum of its local gradients with the G3 received gradients to a sum over G3 and G0 gradients. And after that, we do a quantization on the sum of these gradients, and then pass this partial sum to the GPU1. GPU1 do the same thing, like first do a dequantization, and then a sum, and then a quantization pass to GPU2, so on and so forth. And in order to finish one round of reduced scatter, the number of sequential quantization and dequantization kernel involved equals to the number of GPUs we have. Here we have 4 GPUs, so the number of sequential Q plus D is 4. If we have 1,000 GPU, the number of sequential quantization could be 1,000, which is really huge. So the first problem is we may have too many quantizations sequentially. So how can we solve this problem? Our solution is to directly replacing this ring-based reduced scatter with our one-hop out-wall communication protocol. As you can see on the right-hand side figure, after each GPU generates their local gradient like those gray boxes, we first do a one-shot quantization, and then generate those blue boxes on the right-hand side figure. And after that, we do a one-shot out-wall across all the GPUs we use, and then do a dequantization and reduction to get the final correct answer. By replacing the ring-based reduced scatter with our one-hop out-wall, we can reduce the number of sequential quantization and dequantization from number of GPUs to just one. However, we have the second challenge here is with our one-hop out-wall protocol, it may have an issue of communication volume blow up. As you can see on the left-hand side figure, the baseline ring-based reduced scatter, the cross-node communication volume always be M because all the data chunk follows the ring topology to send and receive. So the total amount of data volume communicated is M. But in the middle figure here, assuming we have n GPUs per node and we have model size of M, in the middle figure here, after each GPU do a local quantization, they can reduce their local gradient size from M to M over 4. But after that, we need to do that one-shot out-wall, which means every GPU need to send out M over 4 data cross-node. So in total, cross-node communication volume can be n times M over 4 because we have n GPU per node. And each GPU need to send M over 4 data. So this is much bigger compared with the original size M. So how can we solve this issue? So we change our plan. Instead of doing one hop, we do a two-hop out-wall. So the step one, as you can see on the right-hand side figure, we do a intra-node out-wall and reduction in order to reduce the communication volume per each GPU. Here we reduce the communication volume per each GPU from M over 4 down to M over 4n. And after that, we will do the internal out-wall. Here, each GPU only need to send out M over 4n data. So in total, each node only need to send out M over 4n times n is M over 4 data. By doing this two-step out-wall instead of one hop, we can remove this communication volume blow-up issue. The third challenge with our hierarchical auto protocol is data misplacement issue. As you can see in this setting, we have two machines, each with two GPUs. After each of the GPU generates their local gradients, like the gray boxes at the bottom, the correct final data placement after our communication should be those green boxes at the top, which means GPU 0 has a gradient chunk 1, GPU 1 has gradient chunk 2, so on and so forth. However, if directly apply our hierarchical auto after the first step, intranode auto, you can see the G1 after the auto happens, the G1 cannot even see the gradient chunk 2, which should be its correct final data placement. Similarly, on the G2 side, it cannot see the gradient chunk 3, which should be its correct final data placement. So because of this issue, after the second round internal auto, we have data misplacement issue between GPU1 and GPU2 here. So how did we solve this? Basically, we try to do something called tensor slice reordering before we do any quantization and any communication. As you can see in left-hand side figure, after each GPU generates their local gradients, what we did is we first swap the gradient chunk within each local GPU. Here we swap the order of gradient chunk 2 and 3 in the reverse order, shown as those orange arrow lines. And after that, we do the intranode auto and reduction. And after that, we do the internal auto and reduction. Now you can see everything just work perfectly and correctly. So the QGZ module overall workflow look like this. Before we do any quantization, we first do a tensor slice reordering. And after that, we do intranode quantization, and then do intranode auto communication as a step 1. And then do intranode dequantization and reduction to get the intranode reduced gradient values. And after that, we do internal quantization, internal auto communication, and internal dequantization and reduction in order to get the correct final answer for every GPU. We further optimize this workflow by doing two things. The first thing is called kernel fusion. Basically, we fill the subsequent kernel together in order to reduce the I/O times of global memory access on the GPUs. Thus, we can improve the system efficiency of the kernels. We do two kernel fusion. One is on the tensor slice reorder and the intranode quantization. The second one is on the intranode dequantization, intranode reduction, and the internode quantization. The second optimization we did is to do some kind of communication collective overlapping. Basically, here we overlap intranode communication and the internal communication on different data chunks, such that they don't have any data dependencies, so we can do the overlapping. By doing this overlap, we can reduce the end-to-end latency. Here comes to the evaluation part. As you can see on the left-hand side table, we focus on small batch size. Here, the tokens per GPU is just 1K or 2K. And we mainly focus on the second column, the low cross-node bandwidth column, which is 1 IB connection between nodes, which means it's just 100 gigabits per second across node. And you can see in the middle column here, compared with our baseline, ZeRO++ can achieve up to 2.16x speed up compared with ZeRO for large language model training. And even for the 8 IB connections as a red column in the table, we can achieve roughly 16 to 30 percent speed up compared with ZeRO baseline. And on the right-hand side figure, we also show the scalability of ZeRO++ from 64 GPUs up to over 300 GPUs. As you can see, both in low cross-node bandwidth, which are the left two figures, and the high bandwidth communication channels, which are shown as the right-hand side figure. In both of these cases, ZeRO++ can achieve higher TPLOPs per GPU compared with ZeRO, especially for the IB equals to 1 cases, the left two figures, we can always consistently have almost 2x speed up compared with ZeRO. We also do some validation loss test to see our model converged correctly. We tested on 2 models. One is a smaller model on the left, the GPT 350 million parameters. The right is the GPT 13B. In both of these cases, ZeRO++ loss curve matches the baseline ZeRO stage 3. And later we also introduced some kind of 6-bit quantization, which is between 4 and 8 bits for some use cases. We also conduct some evaluations on the RLHF training, Llama 270B and OPT30B. As you can see on the left-hand side figure, those orange bars are ZeRO++ throughput, and those blue bars are the ZeRO stage 3. For the Llama 70B, we can achieve 3.3x speed up, and for OPT30B, we achieve 3x speed up. One public announcement from LinkedIn is that ZeRO++ helps them reduce over 50% of the training time in their AI production workload training at LinkedIn. And this is like a LinkedIn post here. And we have like an offline gathering and a talk there at LinkedIn headquarters. The summary here is ZeRO++ incorporates 3 techniques, QWZ, HPZ, and QGZ, to optimize end-to-end communication during ZeRO training, and we reduce 4x communication volume. Compared with ZeRO, ZeRO++ achieve up to 2.16x speed up over 300 GPUs training, and 3.3x speed up over RLHF training. And ZeRO+ already integrated with our open source DeepSpeed repo for the next generation ZeRO training engine. And we are looking for all kinds of collaborators and users. If you are interested, feel free to ping me with the email at the bottom. Thank you.
Nice, Alex. This is incredible work that you guys are doing. What are next steps? So, first of all, you guys have you've invented some of these methods. Right now, you're already using them internally. You see the results with LinkedIn. Are they kind of like broadly available throughout? Is everybody kind of like starting to adopt them at Microsoft, or is it still in like a little bit more of like an experimental phase?
Yeah, in Microsoft, we have some production workload running using ZeRO++. One thing I can say is, for example, the popular small language model at Microsoft called the Phi3 and the Phi4 series, PHI3. Those small language model series, they use ZeRO++ to improve the training throughput. And we also try to apply our method to some internal non-public workload, but that I'm not allowed to say.
We won't press you on that. Question from the audience. Is there a trade-off of reducing training time on model performance?
Yeah, so that's a great question. Usually people believe that when we do quantization, our model, like a model convergence can have a big issue. But what we saw is if we quantize to 8 bits, it is okay, or the fully trained model is usable. Maybe after the model fully trained, compared with training using full precision, we may have the some benchmark score a little bit lower than training using the full precision, but it's usable. And in most of cases, for smaller models like several billion to maybe like less than 200 billion models, in those cases, we never see any correctness issue or performance loss regarding to accuracy. Only very big model have some accuracy loss, maybe over 500 billion.
Alex, thank you very much. If folks have questions, maybe they can find you afterwards or join the chat.